MIMO, Model Predictive Control. Model Predictive Control, or MPC, controls a system with multiple inputs and multiple outputs. It uses a mathematical model using predicted output to set the controller to produce desired results. MPC uses a look-ahead method to optimize output based on knowledge of the process output. Empirical observational studies of various past input-output profile provides a mathematical model. Given an input-output profile up to a time t, the successive iteration of the model, given by equation 2, allows us to predict subsequent output and input behavior of the system. In our optimization studies, we're interested in how the system's actual input-output file, as predicted, compares against a set of desirable input-output profiles, which is given by equation 1. It is important to note that the ideal system input-output model is derived independently of the system's operational limits and goals. As was discussed earlier, equation 1 describes the desirable input-output behavior of our system to achieve goals within its operational limit. Meanwhile, equation 2 empirically predicts the system's future output path based on the system's past input, u, and output, y. Equation 3 compares how our prediction fares with respect to that ideal output given in the first equation. Finally, equation 4 scales the error and predicts a calculated optimized input based on previous calculations. All the equation here only describes the system's input-output behavior for one future time step. We shall see in the next slide how the same model can be iterated to extend our prediction beyond one time step. By repeating steps 1, 2, 3, and 4, we are able to create the input-output profile. Associated with the input-output profile are the errors of each time step. To optimize the system, that is, to minimize the absolute deviation between the predicted output of the system from the desired behavior, we need to define the system's future residual function. The system is optimized by finding parameters that minimize that residual. C relates optimized input value to the error of the predicted output with respect to the desirable output. So, once again, optimizing the system eventually boils down to minimizing the output residual of the system. Mathematically, optimizing the system is to find a fixed value of C. That is, to set the derivative of residual with respect to time equal to 0. With the value of C well defined, our optimized input value is now well defined. We can now say that we have optimized the system.